Welcome to lecture number 9. Today we will talk about periodic signals and we will introduce important definitions, some basic definitions, and then later important stuff like the mean value and the RMS value. Okay, what is a periodic signal? Let's have a look at a voltage, and let's say we have a sinusoidal voltage as we have in our power network at home. So, and a few definitions: the maximum value and the negative maximum value is called the amplitude of a signal. So our first definition, the amplitude. And a periodic signal means that we have a period of time, and after that period the same signal restarts again. And here, if you have a look, we have here our periodic time, and that means after the time called capital T as a variable, the function starts again. Okay, and then I told you we have a sinusoidal voltage in our power net, and maybe you heard we have 50 hertz there. And the periodic time and the frequency are just convertible into each other by the inverse. Okay, and then there is another definition for the frequency, and it is called angular frequency. It's just 2 pi times f. And why do we use that? 2 pi f, or 2 pi divided by capital T. I'm sure you have seen it before. If we define a voltage, we often write it like this. The voltage is the amplitude times sinus of omega t. Okay, why this omega? It's quite convenient because omega is 2 pi divided by capital T. And if you have a look at this function, the sine function is a mathematical function. And for sine of 0, the result is 0. And then the sine function needs arguments between 0 and 2 pi, and then a whole period is finished. And if the argument is bigger than 2 pi, it just starts at the beginning again. Okay, and if we have a look at this function, if we have our time variable t, and t is 0, okay, then we have a sinus of 0, that's okay. But if t increases, then you have there this variable t divided by the periodic time, and that means when our time variable t reaches the value of the periodic time, then we have our sine function of 2 pi. And therefore this angular frequency omega is just a very convenient variable to express the frequency of a sine function. Okay, a next important definition, the mean value. Mean value, when I think back to the first years at school, in my second year in school we had the first tests where we got marks. And then we wanted to calculate the average mark of the whole class. What did we do? We had the results of all the students, and to calculate the average mark, we just added the single marks and we divided by the amount of the students. Today we would write it like this. We have 1 divided by capital N, this is the head count of the students, and then we take the sum over the marks of the single students. Okay, I'm sure you've known that. But now we want to calculate the mean value of a continuous periodic function. Okay, for instance, this one. If you have a closer look, you will see that we have a periodic time, and before and after the same signals just repeats. Okay, and now we want to calculate the mean value. And we nearly do it like before with the countable numbers, but this time we don't have continuous points, and therefore we don't use a sum, but we use an integral. And that means when we use the integral, by the way, the sign of the integral is just a big S, and it stands for sum. And what we do here is, with the integral, we sum up all the infinite points over one period, and then we divide by the period length. And that is the mean value. Why do we need it? I will show you. Let's say we have such a voltage function here. And you see we have maximum value and a minimum value, and it's quite easy to see here we have a mean value. And we can separate this original function into two subfunctions. We have our mean value and we have a pure sinusoidal function here. And therefore, our periodic function can be separated into a direct and an alternating component. And if we think about voltages or currents, then we have a name for this mean value, and we call it the DC offset. Okay, let's come to the next definition, the RMS value. Okay, let's think about a cooking plate. When we switch it on, it gets warm and we get heating power of it. And a cooking plate is just like an ohmic resistor. And you remember from our DC stuff that we can calculate the electric power at a resistor with voltage square divided by the resistor value. Okay, and now let's have a look what happens in our cooking plate or in a resistor if we have AC voltage. So we know in our power net we have sinusoidal voltage, and that means we can calculate the power of the moment with this equation. But at every single moment we have another value of the voltage. When the sine function is 0, according to this equation, the power is 0. And then the voltage rises, and that means that the power rises. The voltage goes down and the power will go down, and so on. And I prepared an animation. In the upper graph we will see our sinusoidal voltage, and in the lower graph we will see the power consumption of our resistor. Okay, you see we have zero power when the voltage is 0, and we have a peak power when the voltage reaches its maximum value. Then the power reduces until we are at the 0 point of the voltage. When the voltage becomes negative, the power rises again because we take the square of the voltage. and that means even when the voltage has its minimum point, we have a maximum point at the power. Okay, think again about our cooking plate. Maybe you do an experiment at home. Go to your switched off cooker, put your hand on a cooking plate and switch on your cooker. And now we just found out that the power of the cooking plate goes from 0 to a maximum value, but then back to 0. Try to feel that. Do you feel that the cooking plate becomes hot and cold and hot and cold and hot and cold? No, you don't. And the reason is that the material of the cooking plate is just too slow to follow the maximum and minimum values of the power, and therefore what we feel will be just the mean value of the power. So therefore we could calculate the power of our cooking plate with our equation for the mean value. Okay, let's have a look when we use it. We have an expression for our power, so let's put it in here. And yeah, I will rearrange this equation a bit. I just rewrite it with a big denominator where this R is in. Okay, this looks quite inconvenient, doesn't it? And now let's think back how it was in our DC circuits. There we had this simple equation and we liked that. And now we are dealing with a periodic voltage. Okay, and it would be easier if we just had a number value for our voltage. We are not interested that we have this in our power net 50 Hertz signal. We just want one value for it. And in our power net, it's this 230 volt. Okay, so the result of this integral will depend on the shape of the voltage, but it will be just a number. And we call that number URMS. And we need URMS square to have the same equation as we had for DC circuit. Okay, and now if we compare it, that means that this URMS has to be the square root of this purple part of the equation there. And this is the reason why we call this value RMS value. RMS stands for root mean square. So we take the root out of the mean value of the square of our voltage. Okay, to say it again, why do we have the RMS value? The RMS value is an artificial value, and we can calculate an RMS value for every periodic signal. And this value says that if we had a DC voltage of the same size, then this DC voltage would produce the same amount of electric power in a resistance as this periodic signal with the RMS value. So if we have a DC voltage of, let's say, 2 volt, then we could calculate the electric power here with this equation, 2 volt and square divided by R. And if we had a sinusoidal voltage here, I take a sinusoidal voltage with the amplitude square root of 2 times 2 volt. Why that? Yeah, we will calculate it in a minute. That leads to an RMS value of exactly 2 volt. And that means that the mean power consumption of this resistor is also 2 volts in square divided by R. So the same as if we had a DC voltage of 2 volts. Okay, and now let's calculate RMS values for important shapes. Let's start with the most important one, the sine function. Okay, we have this function here, an amplitude times sine of omega t, and now we use our equation for the RMS value. So we have to calculate the integral over one period of this function here in square, and after that we take the square root out of it. I will draw this square function here and have a look in the first half period and in the second half period. The function looks the same, and that means that the result of our integral will be the same in the two half parts. And now I'll do a trick, and I just integrate from 0 to the half of the period time, and I know that for the other half the result would be the same, and therefore I multiply the result here with a 2. Okay, and I don't like this integration over sine and square. It's hard to get the primitive of that, and therefore I have a look in a mathematical book, and it says that sine square of x is the same as 1/2 times 1 minus cosinus of 2x. Okay, I will put it in here, and I did it because I know the primitive of 1, and I know the primitive of the cosinus function. Okay, and that means I can find the primitive here, and now we have to put in the border values. I start a new sheet. Okay, we had this, and now in the first step I will rewrite this omega. You remember omega was defined as 2 pi divided by capital T, the periodic time. And yeah, now I can put in the borders. So we have the upper border 2/2. I put in it for t, and the lower border is t is 0. Okay, this leads to this expression, and now let's lean back and have a look. We see we get rid of this t here, and we get rid of these 2's, and we get rid of these t's. And now you see we have sinus of 2 pi, that is 0. And then we have a sinus of 0, that is 0. And okay, there's nearly nothing left, only here this amplitude square divided by 2. Okay, and that is cool because we found the RMS value for a sinusoidal function. It's just the amplitude divided by the square root of 2. Let's calculate some more RMS values. Let's take a triangle function. Same as before, we can use our equation to calculate RMS values. Okay, now let's have a look. I will show you how the square function of our triangle looks like. Okay, and here you see that the area under the function curve will be the same in every quarter of our squared function. And therefore, I will just calculate the integral from 0 to 1/4 of our period time. And I do this because it's more convenient. Otherwise, we had to separate our function for the parts where the line is rising or falling again. And now we just have to have a look at this first quarter where we have a straight rising line. Okay, I calculate the square. And now we have the function t square, and we know that the primitive of that is t in the power of 3 divided by 3. And I start a new sheet. And now I put in the borders and I calculate this power of 3. And now you see we can shorten some things, and what is left is the amplitude square divided by 3, and we take the square root out of that. And that means that the RMS value of a triangle function is the amplitude divided by the square root of 3. And in the end, I want to calculate the RMS value of a square function. This time it's really easy, because if we take the square of this rectangular function, we just get a constant line. So therefore, our function is a constant. That means we can write it in front of the integral, and the primitive of a constant is just the variable itself, and therefore if we put in our borders we get this, and that means that the RMS value of a rectangular function is just the amplitude itself. Okay, and these are the RMS values of our 3 different voltages. And you should know these values. And you should also know how to calculate it, but important is that you know the results of the calculations.